get through all my slides. Yes, the very last thing that I want to talk about, the Ehrenfest classification of phase transitions. So I mentioned earlier, there are first order phase transitions and second order phase transitions, okay? So if we just look really quickly at what happens to all of the properties of a first order phase transition as a function of temperature. So for example, if volume, there's a huge jump in volume. It's discontinuous, okay? Same with enthalpy. There's a huge discontinuous jump in enthalpy. So these lines right here on this graph mark the transition. So we'll say TRS for transition, okay? As it turns out, the chemical potential just falls off smoothly. And that's because if you remember, right, this line for one phase would just continue along, right? And for this other phase would continue along. So the chemical potential just has that sharp point. But just like in enthalpy, in entropy, there's a discontinuous jump in a first order phase transition. And the result of all of this is the heat capacity at the phase transition becomes infinitely large because you are technically supplying heat without a change in temperature. So all of these things, as you might guess, what is a first order phase transition? Well, a solid to a liquid or a liquid to a gas, right? Okay, so these are large scale changes. Right? So in other words, when you look at the entropy change of a liquid to a solid, there's a huge difference. Same with the enthalpy. Okay? Same with the volume, as we just discussed. And so that means the heat capacity for those first order phase transitions is infinite, technically, at that value. So what about a second order phase transition? Okay, well, notice that there's some differences. Right? So the volume, it has kind of this like discontinuous function thing going on, but not this big gap, right? So it's a much smoother change. Same with enthalpy. Same with chemical potential. There's a really smooth change. You can hardly tell a difference in the chemical potential in a second order phase transition. Same with the entropy. And the heat capacity, there is a discontinuous jump, but the heat capacity is technically not infinite at that value, okay? You notice that it actually drops pretty dramatically. So in other words, as you might start guessing, second order phase transitions aren't really these large scale changes. They're actually like solid to solid transitions. So like from one crystal structure to another crystal structure. Okay, so perhaps from like, you know, a BCC unit cell to an FCC unit cell might be a second order phase transition. So very slight changes, right, in the volume or the delta H. So like in all of those water phase, that water phase diagram I showed you, all of those different solid phase transitions, those would be second order phase transitions. Okay, now what about the in-between region? So I'm going to kind of put like a squiggly line. There's an in-between region between first order and second order phase transitions, and I'll call that the lambda line. Okay? And let's go back to helium for 1 second. Let's go all the way back. Yes. Look, here's the lambda line for helium. So as it turns out, the phase transition between a liquid and a superfluid, it's not quite first order, but it's also not quite second order, okay? And the reason why it's called a lambda line is because if you look at heat capacity versus temperature, it actually makes like the shape of a Greek letter lambda in the thermogram. So it looks like it wants to be infinite, but it also quickly recovers. So it's kind of like has some characteristics of a first order phase transition and some characteristics of a second order phase transition. Okay? So the lambda line is in reference to things that are in between. Okay? So definitely from a fluid to a superfluid, fluid to a superfluid is one of these in-between type of phase transitions that would have a lambda line, such as helium. Another interesting example is actually the transition between transitions between ferromagnetism. So there are certain materials that under certain conditions of temperature and pressure can change their magnetic properties. And so that has somewhat similar, ideas of a solid-solid phase transition where it's going from like different crystal structure. But as it turns out, there's fairly large differences in its volume and enthalpy and entropy. Okay, so magnetism would also exhibit a lambda line. Okay, so most of the phase transitions that you've seen up to now are these first-order phase transitions. Okay, when you have these really interesting solid-solid phase transitions, like different crystal structures, those are second order. And these very few rare examples like fluid to superfluid or the change in magnetic properties, those are somewhere between first and second order. And the telltale sign is the lambda line in the heat capacity. Okay. But most of the time, when you're observing heat capacity in a second order phase transition, you're going to see this like kind of discontinuous looking gap. Okay. All right, folks, so I think that covers it pretty well. Hopefully my injured brain was making some amount of sense there. Please reach out to me for questions if you have any. I'm sure you will. I will see you all on our live meeting on Friday or office hours. All right, folks.